Wednesday, but it is solutions. And so we'll do like a little preview here of some of this. So okay, so let's start off with a solution and what it is. So a solution is really made up of two parts. There is what is referred to as the solute, which is the smaller part of the solution. And there is the solvent, which is the larger part of the solution. And solutions in general are really the substances that get the AQ symbol next to it, which is our aqueous. And as we might have talked about earlier, but just in case not, again, there is a difference between aqueous and basically something that is a liquid. So something that is a liquid is just a pure liquid by itself, not mixed with anything else. A solution that gets the aqueous symbol is really when you take something like a pure liquid a lot of times and dissolve something in it. So kind of two things together. And that's why really a solution is a mixture. It's a homogeneous mixture. So for example, if you took some potassium chloride solid and you took some water, which is a liquid, these are each pure substances, but the potassium chloride here would dissolve in the water, and that would give you a potassium chloride solution that would get the aqueous symbol next to it. In this particular case, the potassium chloride, which is our solid we're dissolving, would be the solute. And the water in this case, which would be the larger part, would be the solvent. So solute's always the larger part of this, smaller part of the solution. Solvent's always the larger part. In a lot of cases, water is a very common solvent. That's because it's polar. It's also not very toxic, and it works well with a lot of things. But water doesn't always have to be the solvent, but in a lot of cases, it is. How do you know what the solute is? It's actually the name of the solution. So if you have a potassium chloride solution, the solute is potassium chloride. If you have a sodium nitrate solution, sodium nitrate is the solute. So whatever the name of the solution is pretty much what the solute is. And again, in a lot of cases, you can a lot of times consider water probably a very good solvent for a lot of ionic compounds. It's not a good solvent for all things, but it is a very good solvent for a lot of things. So let's talk a little bit about, sort of that idea and how things dissolve in each other. And the way things dissolve in each other is this idea of what is referred to as like dissolves like. And what that means is these are things that are typically soluble in each other. And basically, if something is soluble, it basically will mix. So for example, if we are talking about two liquids, they will mix together and basically be one looking liquid. Everything, you won't see different layers or anything like that. If we're talking about a solid in a liquid, the solid will dissolve in it. So that's what basically soluble means. And the idea here is things that basically can interact with other molecules the same way they interact with themselves, make them soluble in each other. And it really has a lot to do with those intermolecular forces we talked a little bit about today. So if things have very similar intermolecular forces, they will be very soluble in each other because they basically will be using the same type of interaction as they're very much familiar with. And there's really three types of intermolecular forces. There is what is referred to as hydrogen bonding. There is dipole-dipole interaction. And there's what is referred to as dispersion forces. Hydrogen bonding is used for polar molecules that has an hydrogen bonded directly to either nitrogen, oxygen, or fluorine. So if you have some type of polar molecule, like we were talking about when we were talking about bonding, and it has a hydrogen in there that's directly attached and bonded directly to a nitrogen, oxygen, and fluorine, it will use what is referred to as hydrogen bonding. Dipole is for polar molecules that cannot hydrogen bond. So if you still have a polar molecule but no hydrogen that can do hydrogen bonding, it will use what is referred to as dipole-dipole interaction. And dispersion forces are really the forces that are used by nonpolar molecules. In terms of the strength, it actually increases as you go this way. This is the strongest, and that is the weakest sort of force. So a dispersion force is really the weakest force you could have. They're really temporary forces, and hydrogen bonding is the strongest force that you could have. So the way things basically dissolve in each other or mix with each other is the idea of basically, you could think of them, are they polar? Are they non-polar? And that will tell you a lot as to whether or not things will really kind of mix. So typically speaking, things are soluble in each other if there is something that is ionic and something that is polar. So something that's ionic and polar will definitely mix together. Something that is a polar guy and another polar guy will also mix together. And something that is non-polar and something that is non-polar, those guys will also mix really well together. You really only run into sort of a problem in terms of something being insoluble, which means they really won't mix, is when you kind of cross that over and you try to mix something that is polar with something that is non-polar. So like oil and water, they don't mix, right? Oil will basically float, water will kind of stay on the bottom there. But things like sodium chloride and water, they will mix really well together. Two polar things, you put them together, they should mix and be soluble. Two non-polar things should also be. So why does something, say like potassium chloride that we just looked at, basically are an ionic compound, and something that's polar like water work really well together? It's because water, as we talked about earlier as well, is a polar molecule. Again, the oxygen being more negative, the hydrogens being more positive. And when you put something that's ionic into water, what happens is it actually will break apart into its ions. And what happens is that you have the positive ion and you have the negative ion. And what happens is the waters will actually surround all those guys. So the water here will surround the positive guy with its oxygen, which is the more negative side of water. Opposites attract. And the negative ion that goes for a swim, so like Cl minus, will be attracted to the hydrogen side of water. And this does two things. This basically allows something like, say, potassium chloride to dissolve in water. The water molecules basically surround all those ions, and it actually prevents those ions from coming back together. And that's what keeps it dissolved, because there's a lot of water molecules and stuff like that. So that's basically how something just dissolves. It's actually why when you dissolve something, it actually is just a physical change because it's still there. So if you ever evaporated off, again, water from, say, salt water, what you'll be left with is the salt is still there. You just visually cannot see it because there's lots and lots of water molecules surrounding each of the ions, and you no longer can visually see it because there's just a lot of water molecules that are there. Any questions on that there? So when we talk about solutions, there's a couple of different types of solutions that's important, and we'll talk about some of those, which I think is maybe in the lab here today. And that has to do with the idea of what is known as electrolytes. So electrolytes are substances that basically go for a swim and they break apart into ions. So if we look at electrolytes, which are substances that dissolve in water and produce ions, which is very important for electrolytes. So there's a few different types of electrolytes. There's actually strong electrolytes. So strong electrolytes will 100% break apart into ions. In solution. So if you have something, say like sodium chloride that's dissolved, a sodium chloride solution, in that actual solution, you will have 100% the sodium ions and the chloride ions floating around. So 100% when you have a solution of sodium chloride, what you have floating around in there are sodium and chloride ions. You have none of the actual sodium chloride units still together. It will completely 100% break apart into those ions. And that is why it's referred to as being a strong electrolyte, because pretty much it all basically breaks apart. The result of that is you now have a solution that has a lot of ions that are floating around in it. And solutions that have a lot of ions floating around in it helps complete sort of the electrical charge, if you will, and it will conduct electricity really well. So this solution will conduct electricity very well. So I think maybe this is the lab or not, but a lot of times they'll take like a light bulb, for example, hook it up with a couple electrodes and you stick it in the solution. And if you do that, what you would see is the light bulb would be very bright. And it's going to be very bright in that case because it's conducting electricity really well. And it will go off and obviously be very, very bright. So two ways that you could recognize it, something as a strong electrolyte, is pretty much a one-way arrow. And you start with an ionic compound on the left and you end up with the ions on the right. And that definitely is a strong electrolyte. Also, if you have the advantage of watching that sort of experiment being done, you do it with the light bulb and the light bulb goes off very brightly. That is definitely a strong electrolyte. Any questions on that there? Now, a weak electrolyte is a little bit different. A weak electrolyte will mainly stay together but will produce a few ions. So unlike a strong electrolyte, which pretty much as soon as it goes for a swim will produce a bunch of ions really quickly, and that's pretty much all you got. In a weak electrolyte, it actually will stay together, but it will still produce a few ions. So for example, if you took something like nitrous acid, which is a weak acid and also a weak electrolyte, when it breaks apart into H plus and NO2 minus. And in this case, in solution, you mainly have this guy still together. So you actually still have this guy together. And you have a few of these guys formed. So unlike the strong one, in this solution, you pretty much have a lot of the HNO2, for example, still floating around in the solution. But you will have a few H pluses and some of the NO2 minus guys kind of floating around as well. But a majority of it will stay together. And because a majority of it will stay together and you're only producing a few ions or so in solution, it is still able to conduct electricity, but not as strong because there is not as many ions basically floating around in that solution. So still able to conduct electricity, but not as strong as a strong electrolyte. What's that? It will conduct the thing, electricity. Thank you. That's my wrong one. Thank you. It will conduct electricity. There you go. But not as strong as a strong electrolyte will. So if you did the light bulb and you put the electrode in with the light bulb would turn on, but it would be very dim. So it'd be very dim, but the light bulb will turn on almost like it's losing power and it's going to about ready to shut off. But you will still see it kind of light up a little bit. And that's because there's still presence of ions in that solution. So it is still able to conduct electricity, but nowhere to the extent a strong electrolyte can conduct electricity. So how could you recognize a weak electrolyte versus a strong electrolyte? There are a couple really big hints. And the first hint is really the arrows. The arrows that head in both directions imply that this is what is referred to as a reversible reaction, which means there is sort of a forward direction that goes to products, but at some point, some of those products will come back the other way and make your reactant. So it's really like a two-way street in terms of that reaction. It goes one way and comes back the other way. So if you see a reaction that's written with those arrows, with a guy on the left and then some ions on the right, you know it's going to be a weak electrolyte. Also, if you have the benefit of looking at, again, the sort of light bulb example, and the light bulb only kind of goes on very dimly, that is going to be a weak electrolyte for sure. Any questions on that one there? The last sort of electrolyte, I guess, is what is referred to as a non-electrolyte. And a non-electrolyte is actually something that will dissolve. So a non-electrolyte it will dissolve, but no ions are produced. And it's really because there's no ions that are produced in this case, it will not conduct electricity. So if you put your light bulb sort of example in there, it will not go off. And an example of that, for example, is something like sugar. You know, you could take some solid sugar and put it in some water or something like that, and you'll end up with sugar on the other side that's dissolved. Sugar is carbons, hydrogens, and oxygens. Those are all non-metals, which means as a covalent compound, there's sharing of electrons. There's no ions that will basically be produced. So even though it will dissolve, because there is no ions that are present, it will not conduct electricity, and is what is referred to as a non-electrolyte. Any questions on those three things there? So another important thing of solutions that we deal with is what is known as concentration. So concentration is a way that we sort of represent how strong or maybe how weak a solution would be. So let's talk a little bit about some concentration units and some common concentration units. Probably the most common unit of concentration is what is referred to as molarity. And molarity is abbreviated with a capital M. And what molarity basically stands for is the moles of the solute divided by liters of solution. And most people just go, molarity is moles per liter. You could kind of think of molarity as a formula, and much like the density one, we oftentimes could use it in kind of three different ways. We could use it like this to solve for the molarity. You could also solve for the volume in liters, and that would be the moles divided by the molarity, which is a very common sort of use of it. And lastly, you could actually solve for moles by taking the liters times the molarity. So again, molarity is moles per liter, and that's sort of three different ways that we do use that sort of relationship. When you do calculate the molarity of something, the number always stays with the moles part, and it's always 1 liter. So the number kind of stays with the moles part, and it's 1 liter. It's kind of similar to how you calculate molar mass, where the number stays with the grams, and it's always 1 mole. So it's kind of a similar sort of idea. Now, when we say we have 1.25 molar potassium chloride solution, what that basically means, and whenever you do sort of calculations that involve molarity, it's a very common mistake that people make is that they leave the units as big M. And I would highly recommend that you don't do that, because very commonly people have no clue about the liters part of it, like where it is, or what you should do with it. So when you have something that has a molarity like this, I would convert it into really like a conversion factor that you could use in a calculation. You could say that there is 1.25 moles of KCl in a liter. Or if you needed to use it like a conversion factor, you could flip it around and say in 1 liter, there is 1.25 moles of KCl. And I would highly recommend that you kind of use it like that and use it like a conversion factor. Again, it's very common. People just have no idea about the volume part or anything like that. It's also really important that if you do have a volume and you're doing this calculation here, whenever you're using molarity and volume together in this situation, the volume does need to be in liters. So a very common mistake that people make is they do not convert it to liters before they multiply it by the molarity, and they'll end up with really not moles. You'll end up with something else. So always make sure it's in liters. When you multiply it by molarity, you'll be in good shape, and you want to kind of use that as a conversion factor. So for example, if we had, say, what is the molarity of a solution made by dissolving 32.6 grams of KCl in enough water to make 255 milliliters of solution. So why don't you give it a try? I'll give you some numbers here. Potassium is something 3910. And chlorine is 3545. All right, so see what you come up with here. We're looking for what is the molarity here. It means basically moles per liter. So really we need both of those guys in those units. In this case, we have 32.6 grams of KCl, and we have a volume here of 255 milliliters. So we do need to do a little bit of work. We basically need to convert our grams into moles, so we can put it here, and we need to convert our volume from milliliters to liters. So I'm going to do that one first. In this particular case, that means there is 1,000 milliliters in a liter. The milliliters here will cancel, and that gives me 0.255 liters. So that again is what's going to go into our bottom. To convert our grams into moles, we once again use the molar mass from the periodic table like we talked about previously. In this case, we just need to add it together. So the molar mass of KCl would be our 3910 grams per mole plus our 3545 grams per mole. That's going to give us 3545 plus 3910. Going to give us 74.55 grams per mole. Remember, we're going to use that as really a conversion factor here. So we're going to go with 32.6 grams of KCl. We want to get rid of grams, so it's going to go on the bottom, 74.55 grams per mole of KCl. Grams will cancel. 32.6 divided by 74.55. Going to give us 0.43729 moles. I'm going to take it to a few digits here. And that is the other missing piece that we need basically to calculate the molarity there. Now that we have it both in moles and we have it in liters, the molarity will be our moles, 0.43729 moles, divided by our liters, 0.255 liters. And if we do that, ends up with a 1.71. The units here are going to be moles per liter, or you could write 1.71 big M. You could also put KCl there if you like as well. So either one is fine in this particular case. Yeah. Question on that conversion there. Again, we do use this molarity as sort of like a formula. We can solve for molarity like we did in this problem. You could be given the molarity and the volume and need to solve for moles, or you can have the moles and the molarity and solve for liters. So we can solve for really any of those three things sort of in that molarity sort of formula. Any questions on that? Again, I would highly recommend kind of doing it like this, so you can kind of see all the units, kind of do a dimensional analysis way so you don't miss out on any unit. Again, when you see the big M, that is molarity, not just moles, which is a very common mistake that people make as well. Any questions on that there? Okay. The next thing is, I put it down somewhere. I put it here. There it is. All right, another type of unit which I think that's in that sort of lab is percent by mass, so percent mass to mass. And that is the mass of a solute divided by the mass of a solution times 100%. So I would say molarity is probably the most common, but occasionally solutions are given in these sort of percent concentrations. And the important part of this sort of formula is actually the bottom part. So you do have to remember, as we talked about a little bit earlier, that the solution is two parts. And you want to make sure that you get both the mass of the solute here plus the mass of the solution. I'm not the solution, I'm sorry, the solvent there. Too many S's. Let's try that again. So it should be the mass of the solute plus the mass of the solvent. There we go. And the reason I say you want to make sure that you do it, it's very, very common in this sort of problem where you would use this formula that they kind of give you that information separate from each other. So a lot of times they'll give it separate. And it's a common mistake that people will make is that they'll just use the mass of the solvent rather than both of those things together. So you do want to be careful when you're doing a problem that involves percent by mass to make sure that you do get both of those things. So for example, if we made a solution by dissolving 10.5 grams of KCl in 135 grams of water, what is the percent by mass of this solution? So if we were to look at this, we want to look at two things. First off, we want to maybe identify what is the solute and what is the solvent. The solute in this case, which would be what thing? Solute would be, it is the KCl, it's the smaller part here. So this would be our solute. And our water here would be our solvent. So if we were to calculate the percent by mass here of this solution, it would be the mass of the solute, which is the 10.5 grams, divided by the mass of the solution. And here we would want to take 10.5 grams plus the 135 grams and times it by 100%. This is going to give us the actual solution, both the solute and the solvent together. Again, if you divide by just the 135, you're dividing by just the solvent, and you will not get the right answer. So again, it's very common in these type of problems that they're separate from each other. So we would take 10.5, we would divide it by 10.5 plus a 135 and times it by 100 to see how I did in my made up number here. We will end up with 7.22% by mass KCl solution, basically. So this type of unit is not too bad. That is usually the common sort of error that people make, is that they just divide by the solvent and don't actually get both parts of that solution together. Any questions on that there? Now, if you are given a sort of percent by mass of a solution, you could use it like a conversion factor, just like we kind of talked about using the molarity as moles per liter or liters per mole. You could actually turn that percentage into sort of a usable conversion factor. So we'll just take this example here that we just did. So if we did have something given to us like 7.22% by mass KCl solution, we could turn this into sort of a usable conversion factor by assuming 100, right? So when we have a percentage, the best thing to do is assume that you have 100 of something, because what that does is basically keep the number the same. It doesn't change anything. So what this would mean if we wanted to kind of turn this into a usable conversion factor is, if you had 7.22% by mass KCl, that would mean you would have 7.22 grams of KCl in 100 grams of solution, or in 100 grams of solution, you would have 7.22 grams of KCl. So that is a way that you could take like a percentage and convert it into a usable conversion factor. So for example, if I said I had 62.5 grams of KCl, how many grams of solution would that be? And if we had obviously this percentage of a solution, we could just do a dimensional analysis type of approach, 62.5 grams of KCl. We would use the conversion factor here on the right, so everything cancels out. And that would tell us that in that 62.5 grams of KCl, we can make basically, grams of KCl will cancel. We'll take our 62.5 times 100 and divide it by 7.22. We can make approximately, we'll call it 866 grams of solution from that. So a very common way we sometimes will use percent concentrations like this is really just as sort of conversion factors. And again, you could just turn it into a usable conversion factor by assuming that you had 100 of something. Any questions on that there? The last thing here is dilution. And in a dilution, sometimes we will take a more concentrated solution and dilute it down. And in a dilution, the only thing that we are adding is more solvent. And in a lot of cases, that pretty much means more water. Again, not in all cases, but usually that's what that means. So when we dilute something, what we're essentially doing is it will lower the concentration, like the molarity. And the reason it does that is molarity, if you remember, is our moles of solute per liter of solution, which means when we add more solvent, the only thing that's changing is actually this part of it. This is the only thing that changes when you add more solvent, is actually the liters of solution gets larger. And when the liters of solution gets larger, just mathematically speaking, this number on the bottom gets larger, the molarity then would go down, just mathematically. Small number on top, larger number on the bottom, smaller overall number. So the molarity will basically come down because of that. there's actually a formula that's used to help you in a dilution, and that is what is referred to as M1V1 equals M2V2. And this is the more concentrated solution. And this is your diluted solution. And M here on both sides is molarity. So this is the molarity, or moles per liter. So is this, that is our moles per liter. And volume here is the volume. So V1 would be the volume of the more concentrated solution you would take out to make it. And V2 would be the total volume of your diluted solution. This is the only place really where, if you're using this particular formula, you could leave the volume in milliliters. As long as it's milliliters on both sides, it will work out okay. But if you want, you could convert it to liters here on both sides, and it'll be okay as well. But this is the only place where you can actually leave the volume in milliliters as long as the molarity is there. And that is because, just so you know, when you do take something like milliliters times the molarity, you actually get what are known as millimoles and not moles. And that's why usually you want to take liters times molarity, because that will give you moles, which is actually what we're looking for. But in this particular case, because you have milliliters on both sides, it will actually become molarity back again. So it's actually okay only in this equation, if you use it, to leave the volume in milliliters on both sides. If you're not sure about that and you want to be safe, just convert everybody to liters and you'll be fine in either case. The only difference is, if you use this equation, you convert them to liters and you solve for a volume, you'll end up with liters. And if you leave them in milliliters and you solve for the volume, you'll end up in milliliters. But again, this is the only place where you can kind of leave it in milliliters, it'll be okay. If you're not using this equation or a dilution, you 100% should convert it to liters and use it with molarity. So if it's just molarity by itself, not a dilution, not using this equation, you absolutely should always convert it to liters. So like I said before, if you just want to convert it to liters and not worry about it, use it in the right situation or the wrong situation, just convert it to liters and you'll be in good in all situations when you're dealing with molarity. Any questions on that there? All right, I hope that covered most of this stuff off the top of my head. Yeah, okay. So hopefully that was